Okay, so we talked about, yes, be quiet. We talked about the area under the curve and how could we estimate the area under the curve. And we said, okay, well, Remon said, okay, I don't know, but it looks really good if we put these rectangles under there and we can estimate the area under the curve. And then from the little calculus in motion thing that we saw yesterday, we saw that you can get the approximation closer, by doing what? Smaller rectangles, which means more rectangles, right, in the space provided. So if we think of, and we said that it was kind of like a limiting concept, right? Okay, so the area under the curve is actually, in math terms, the integral. This is the area under the curve. It's actually an S. No! Who told you to ask that?
What is it?
Let's hear it. Who was it? Was it Brian Pico? Because he's on my list.
What did he ask?
Okay, so nothing. He didn't ask anything. He's speaking heresy.
Wait, no, I want to learn.
He'll tell you later. Okay, good. Yeah. To be more like Jesus. No. Okay, here we go. The integral is the area under the curve. Now look at this. F of x is like the height of the rectangle. Dx is like the width of the rectangle. For those people who think it is not important to have dx also, let's just get this discussion over with right now. If you're adding up a bunch of heights, I don't even know what that means. So what we're trying to add is a bunch of areas of rectangles to equal the area under the curve. Okay, so this is the width, and this is really small. It's infinitesimal. Well, I don't know how to spell that, so we're going to write really small. Sorry. Really, really small, because we're getting infinitely many of these rectangles, so this width is basically going to 0, and we denote that with dx. Okay? A to B is the interval. So these are like all the little rectangles, and the reason this is like an elongated S is because we're adding them all up. What's a word for add? Y'all are so smart. Sum. So we're like adding them, all these little rectangles up. Okay. So this is actually equal to the limit what'd you say? I don't know. Okay, so we have the limit as n goes to infinity. N is the number of rectangles. I don't know why it's like that. Here, this one works a little bit better. Limit as n approaches infinity of the sum, this is like a sigma, of I equals 1 to n of f of x sub I times delta x. Okay, this part right here is the same thing that we were putting in the calculator as sum, sequence, f of x, start, stop, all that. Okay, this right here is a sequence notation. So basically what this is saying is we're going to put in our sequence terms into the function. And that's what we do when we evaluate these. Like think about in your calculator when you put all this stuff in, and we talked about how it's just your calculator spitting out numbers. It's saying, okay, I'm going to plug into the original function, I'm going to plug in 1, 2, 3, 4, or 1, 1.5, 2, 2.5, or whatever you tell it to do. I'm going to put in those sequence values. So this is like generating a sequence, and this is adding up all the terms of the sequence. So this is the sum part, this is the sequence part, and the delta x is going to be the width of the rectangles. So this is just a math way to write what we've been doing, what you were doing in your calculator. Alright, so the limit of this whole thing is n goes to infinity. Remember, n is the number of rectangles, so as the rectangles go to infinity. Make sense? Okay. This is actually the definition. Do you remember how when we did derivatives and we did the limit as h goes to 0 at f of x plus h, blah, blah, blah? Okay, that was the actual definition of a derivative. This is the actual definition of an integral. The difference is for derivatives, we found derivatives using the definition, and we're only going to do one integral using the definition because it's horrible. It's not that bad. I shouldn't tell you it's horrible. It's just a little bit challenging. Okay. We're not going to do today, though. Okay, so for example, approximate the integral from 1 to 8 of square root 1 plus x dx with m10. And this will kind of give us a chance to go over these midpoint sums. Okay, so I'm approximating the integral. Remember that the integral is the area under the curve. So basically I'm just saying approximate the area under the curve of this function from 1 to 8 with m10. It does. Okay, so root 1 plus x actually looks like this. From 1 to 8. So I'm talking about this area in here. That's what I'm trying to approximate with m10. Okay, so the first thing I need is how wide are these rectangles going to be? No, close. Yes, which is 7 over 10. So remember that the change in x is always b minus a over n, where n is the number of rectangles. So b 8 minus 1, b minus a over 10, because we want 10 rectangles. Does everyone see that? Okay. Now, times, I'm just going to do the calculator notation. Sum, sequence, the function, which is root 1 plus x, the variable, which is x. Now we have to figure out where are we going to start, where are we going to stop. No. But if you're not allowed to use your calculator, it'll be like L4 or L2. It'll be a pretty easy calculation. No, I was just defining this. So conceptually, we talked about how the rectangles are going to infinity. So this is just actually writing that out. The technical math way to write this out. But we're not going to use it today. The only part of this that you have to know today is that the integral is the area under the curve.
So how do you know that she's continuing to write it?
Because I said approximate this with M10. A midpoint Riemann sum with 10 separate intervals. Yes. Yes. Okay, now where are we going to start? So if you think about the first rectangle that's going to be there, it's going to start at 1, and how long is it going to be? Huh? 1 plus 7/10. It'll be 1 to 1 plus 7/10. Okay, now for midpoint, we're going to take the middle x, and that's where we're going to evaluate the height. So what is the middle x right here? It's 1 plus half the interval. How long is the interval? 7/10. What is half of 7/10? 7/20, yes. So this is going to be 1 plus 7/20. That's where we're going to start. See what? It's awesome. It's beautiful. Just like that. Just like that. 1 plus 7 over 20. You could.
Why are you starting there?
Because this is a midpoint Riemann sum. We're sort of going over midpoint while we do this. Okay, normal is not the right way to ask that question because yes, if it was L, then you would start at 1. You would start at 1 and 7/10. See, this is the first, okay, I drew this like a little sketch. This is the first rectangle. The first rectangle is going from 1 to 1 plus 7/10. If you're doing a left-hand Riemann sum, you're going to start at 1. If you're doing a right-hand Riemann sum, you're going to start at 1 plus 7/10. If you're doing a midpoint Riemann sum, you have to figure out, okay, what is this middle point?
So if you're doing a right Riemann, then you would do 1 plus 7/10. What was the last one?
8.
This is the right side of that block. If you did the left side, when you start with 1 and then start with the other side.
Then it would be 8 minus 7/10.
Okay.
Okay, but for middle, you're always going to pick the middle one. So 1 plus 7/20. Okay, now where is this going to end? You could. It's going to be 8 minus 7/20. That's where it's going to end. To be the last height you want to calculate. And then this last part over here is the change in x. And what was the change in x? 7/10. Okay, go ahead and plug this in your calculator just for extra practice. Let's see what you get. You're not complaining, right? I didn't think so. You don't have a calculator? You really should just get one. Have you checked the front office? You checked in here? And I told you no?
How do you type all this stuff in again?
You can make sure that one of these doesn't belong to you, but I don't think these are... Oh, it was like that? Yeah. Oh, wait.
No, have the light back there.
Stop it.
That's unfortunate. Here, you can use this one for now.
I cannot concentrate because my number is out.
Oh, it doesn't have batteries. Just kidding. You could use this one if it had batteries.
I literally tried.
Here, use this for now. This one is okay, what did you get? What did you get?
16.11.
Wait, hold on. Did y'all multiply by this 7/10 on the outside?
Yes.
16.118. That sounds good. What did you get? Oh, did you round? Huh? No, it has to be 3 decimals. Okay. All right, 16.118. Did anyone get something else? What'd you?
18.25.
Do you got syntax? If you bring me your syntax, I can help you.
10.2.
Okay.
Okay, now I got it. Now I got it.
Awesome.
I just didn't put parentheses around the 7.
Oh, you did 8 times 7/10, not 8 minus 7/20.
I did that already.
No.
Oh, it's not.
This should, right here, should be a minus, not a times, and this should be 7/20.
Oh, it takes a long time to find the sum.
That's not so bad. Oh, right.
Okay, are we good?
That's. Is that it? Yeah.
No, that's not it. That's it for that problem. We have 2 more examples left. Is everyone good with this?
I'm almost done. I'm on 1+1.
I used to have some in my purse. Okay, perfect. All right, so now you're going to see maybe one of these on your homework, but I did want to talk to you about it before you saw it. This question will say, write as a definite integral. So it's giving you the definition of the definite integral, and you put it in definite integral form. All right, so we know we're going to do the integral. Yes. So just in this form where we have the integral sign and all of that. So we have the integral. What are the bounds going to be on the integral? 0 to 3, because that's our interval here. Okay, what might our function be? X squared plus 1. And then what do we do about this change in x? As n goes to infinity, what does it go to? Dx. Yeah. It goes to some infinitesimal change in x, so that's going to be called dx. So, yes, we think about change in x as some substantial change in x. So, anything that's larger than infinitesimal. So even if it's like 0.000003, we're still going to think of that as substantial. But as delta x goes to 0, then it becomes dx, which just stands for some infinitesimal, almost 0, going to 0 change in x. All right, so that's all we had to do. So write an integral form on that one. Okay, last example. Oh no, it's not very long. Okay, here we go. I'm going to put it on here though, and if you want to copy it down, you can.
Okay, so why do you put dx, but then when you do the sum, you have to put x?
Because in an integral, it's talking about as the number of rectangles go to infinity. In the example where we did M10, we were just saying, okay, we're only going to do 10 rectangles. So only doing 10 rectangles, you know the width is going to be 7 over 10. But doing infinitely many rectangles, the width is going to be like so close to 0, we're going to call it dx. Okay, so this says the graph of f consists of straight line segments from the origin to 1, 1. From there to 2, 0. Then there's a semicircle above the x-axis of radius 1 centered at 3, 0. And then there's another circle below the axis centered at 5, 0. Again, radius 1. That's terrible. Should match the other ones. There we go. Okay, and then I can ask you, what is the integral from 0 to 1 of f of x dx? Now, what do we know, what do we understand this to really be asking? What is the area under the curve from 0 to 1? Now, since this is a geometrical shape, we can find it. What is it? What's the area? A half. It's going to be base 1, height 1, so 1 times 1 times a half. From 0 to 1.
So if it says from 0 to
It would be 1. Okay, now we're going to do the integral from 0 to 4. Okay, so from 0 to 2, the area in here is 1. From 2 to 4, this is a semicircle, so it's going to be pi r squared over 2. But what is r? 1, so just pi over 2. So the integral from 0 to 4 is going to be 1 plus pi over 2. Well, then there's a new question from 0 to 4. No, it's 2 times 1 times a half. Okay, so now what if I asked you from 0 to 6? So we already know that this is area 1, this is area pi over 2, this is going to be a semicircle with still radius 1, so what is the area going to be of that? Pi over 2. Now, since it's below the axis, we're going to call this area negative, so negative pi over 2. Right, so the area from 0 to 6 is just going to be 1. Anytime we have the function above the x-axis, the area will be positive. If it's below the x-axis, the area will be negative. And basically, it's just a directional type thing. Make sense? Okay, that's it for today. You can start on your homework. And I actually have